Back to the channel again. I know it's been a very long time that I've made a video, but anyhow, let's get back into the subject and start to learn what's new around us. And we'll see an important concept called multiple access techniques. So, what is meant by multiple access techniques? So, to understand this, we need to know why we need to understand this, why we need to learn this. Let's take there are many service providers like Jio, Tata, Docomo, Airtel, and many other things. They buy spectrum and they give people the availability to use the spectrum so that we can efficiently use the data and we can access YouTube, Amazon Prime, Netflix, and many other surfing things. So for all these applications to be used, we need data, and if we need data, we also need the good speed, and we also need to have a good bandwidth. Now there are many people around the world who are using Jio, Airtel, Tata Docomo. Now these service providers have to provide this bandwidth so efficiently that everybody in this world has to use it properly. Everybody in this country needs to use this bandwidth so efficiently so that everybody can use it and have the good streaming quality at the same time. So this is a little background that we need to understand before going to multiple access techniques. So the name itself says multiple access techniques. So if everybody is able to use the available bandwidth for their streaming, for their using, for their web surfing, is what something creates multiple access techniques. So let's get into the subject right away. So why do we need them? Just now I told, for many people, for many users to use the efficient data for their web serving, for their YouTube, and for their communication and all, we need this multiple access techniques. It's like everybody can use the available bandwidth. And how better we understand the concept, this is what we need to understand. Now before understanding this, we need to have a little overview. This is my point of view of explaining multiple access techniques. Before that, we need to go through a little basics of how we need to understand this multiple access techniques by understanding the time domain, signal analysis, frequency domain, modulation, analog and digital modulation, baseband and bandpass modulation, spectrum, and bandwidth. And then we need to have this question: why do we need to efficiently use the bandwidth? What is the relationship between bandwidth, data rate, and speed? And what's multiple access and its examples like FDMA, TDMA, CDMA, OFDMA. Now all these things will be covered in the further lectures. Today we'll be dealing about very basic things called as time domain and frequency domain, and little bit further if something permits, if time permits. Now let's have a little quick peek into the basics. Now before understanding what is actually happening, we need to understand what is meant by time and what is meant by frequency. So in order to have this time and frequency analysis, we need to have a little understanding on what is a process and how well the process is being defined. So what I'm trying to tell here is, in the last videos that we have seen that what is meant by time and frequency in a very layman analysis. But today let's see what exactly is time and what exactly is frequency, adding little mathematical concepts to it. So what is time domain? As I said in the previous lectures that I've told, so any process that is represented taking time as reference is represented as time domain. Now let's take, there are many processes that are happening around us. They may be periodic, they may be aperiodic. Let's take sun rising. This sun rising in the east is a periodic process that happens every day in the morning. As well, sun setting happens in the west, that happens periodic. Now are there any periodic things that happen in a day-to-day life? Yes, going to office, going to school, having this college timings, it's all periodic. Now in order to represent this process in a way that we can understand, we take the help of mathematics and we put this process in a formula. Now this formula explains the understanding of the process in a better way. To have this process, to understand this process, the basic thing that we can start over with is a sine wave and a cosine wave. Now this sine wave and cosine waves plays an important role in this nature to analyze and understand the things that are going around us. There are many periodic waves, there are many aperiodic waves which doesn't even represent a mathematical form but also represents the process around it. Now going to understand a graph in a very more clear way, We can take an example, we can take example of many physical processes that are happening around us. Let's take this sine wave. Now this sine wave, as you see, is a 2D wave, but if you see in a 3D, the graph is actually different. It actually varies with time, x, y and z axis. Time and the space is also included in it. Now let's take a very simple example of y equals to mx, a straight line passing through an origin, and y equal to mx plus c has something like this, an intercept. Now looking at this, everybody can say that this is a straight line passing through origin and straight line which is not passing through origin but has an intercept. But how well can you understand this using a process? Let us understand this by taking a vehicle. Now if this vehicle is passing through some city. Now if you see this x-axis and if you see this y-axis, let's consider this x-axis as a time at which this vehicle is moving, and let's consider this y-axis as a speed of this vehicle moving. As soon as, let's take, looking at this x-axis, as soon as the vehicle starts moving, the speed rises. So here there is no point, there is no speed restriction. So vehicle speed rises as soon as we move. There is a linear relationship. So how much far we go, that much speed is going to increase. So we can consider this as a racing car in which as the time passes, the speed of the car increases to a certain extent because it has to win the race. Now let's consider this. The second thing, which is y equals to mx plus c, has an intercept c. Now how well can you understand this with the process of taking a car as an example? See here, there is intercept c. There is some constant gap on y-axis. Since we considered y-axis as speed, there is a little tolerance for this speed. So there is a threshold value for this speed. Even only when there is a c amount of speed magnitude, then only the vehicle starts moving. So until c is 0, this won't start. Or you can also understand that as soon as the time is passing, it is not starting from 0, it is starting from some magnitude of speed. So these graphs do actually represent a process which is considered to be a signal. Why I am calling this signal? Because every signal represents a mathematical form. In mathematical form, you represent it taking a mathematical formula. Now there is another context of representing a phenomena. Now this phenomena can be represented, the phenomena that is represented using a mathematical phenomena may be possible, may not be possible. So there are some things which you cannot represent through a mathematical formula. There are many complex processes in this world, like a random person going to a school or just throwing a dice. These concepts, which are very random, cannot be represented using a signal. That is why we go with probability and probability concept. Whenever a random thing comes, we go with the probability concept. Now we need to understand what is happening around, and to understand it in a better way, we have to analyze it somehow. So let's take so as we have discussed, we have a signal and then we need to represent it through a mathematical formula. Do you think that all the signals that in the nature are periodic? No, absolutely not. Anything that you hear, anything that you see around having some process is completely random. Now let's take, I'm talking to you and then you are able to listen. There is a whole lot of process in between them. Like what I'm talking is being converted into voltage signal, and then there is a process of modulation, and then networking, and then there is some whole lot of stuff of my speech reaching to you in YouTube. Now the main important thing is, if you see a time domain signal, are you able to understand what is happening inside it? No. If it is periodic signal and it is well defined, you can understand what is happening. But there is a lot of difference between time and frequency. If you are able to understand the information content present inside a time domain signal, that is what you call as a frequency domain. But what is meant by information inside a time domain signal? This is a very complex question we need to put ourselves. So what is frequency domain? What is the information content present inside a sinusoid? Now this is absolutely an important question and we need to take care about this. To understand that frequency domain, let's start our analysis with a very simple periodic concept called sunrise and sunset. Now What I will do is, I will take a little example of this sinusoidal signal and explain what is actually happening and how well we can go to the frequency domain. Let's take this sinusoidal wave is a representation of a periodic process in the nature. Now I told a periodic process in the nature is sunrise and sunset. Now this sunset and sunset has a meaning. If you understand this in a very basic way, you can understand the frequency domain in a higher level. Let's take this is sunrise, and this is sunset. Let's take this is afternoon. This portion, I'll take another color. That peak portion is called, let's take this is an afternoon, and then this is night. Okay, this is another portion. Okay, now let's take this is one day. Let's take this is one day. Now during this day, initially sun starts to come out, and he comes out, and then till it becomes this afternoon. So his intensity starts to grow as the time passes. As the time is passing, his intensity is growing till afternoon. And let's take this point is evening. Now from afternoon to evening, the intensity of sun comes down because it's setting. Now from evening to night, he has to decrease, and then his intensity should slowly increase. Till evening his intensity will be down. From evening to night his intensity will still starts to come down, and then he has to come to a point where he has to maintain his intensity for the next day. So it's like the sun is rising and decreasing its intensity with respect to time, and it's coming to the same point as this. So his intensities are increasing with respect to time and decreasing by time. Now this happens every day. But the temperature will be different. But the only concept is sun rising and setting is the main concept. Now this is a process where sun is setting and rising. And I represented this taking a sine wave so as to represent that this is a periodic. Now how can I explain this using a mathematical? There is a formula called as let's take y-axis as yt. Let's yt is equals to ac cos omega t plus theta. Since there is no phase, theta is 0, omega is an angular frequency represented in radians per second. That is mathematical way of representing a signal which is called sine. But sine represents to a periodic nature. Now to understand periodic nature, I have taken sunrise and sunset in a simple way. Now to understand frequency, in last video I have told like frequency is how many times your process is happening. So how many times this process is happening, sunrise and set? It's one time per one day. So the frequency of the process of sunrise and sunset is 1 actually. Now to represent in a frequency domain, we take frequency axis, and let's take this as amplitude. Now this amplitude is I'm taking to be sunrise and sunset. Now how can I graphically represent this? The frequency of this process to happen of sunrise and sunset is 1. So the frequency of happening the process is one time. So I wrote one time, and what is the frequency or the magnitude is sunrise and sunset. So the frequency of this process happening is one time. That is what the frequency. Now this is a very basic understanding of a frequency. So this is a process we represent using a graphical way for our better understanding, which can be represented using a mathematical formula. And now this mathematical formula can be explained in a frequency domain by understanding how many times the process is happening. The process of sunrise and sunset is happening one time. So that's why I drew an impulse. This impulse is having another big story that we'll not be discussing right now. But you understand, if you find sine wave in your nature, you understand you have to represent it with respect to an impulse. An impulse is like a sudden change. Now this impulse represents this concept what I have discussed. Now as I have told you, time and frequency has a very big variation. Now frequency domain has the information content inside it, whereas a time domain doesn't have any information inside it. Now frequency domain, we go with frequency domain because it's much easier to understand the information contents in the time domain signal. Now what is the meaning of this statement? Information content inside a time domain signal. I'll go with this. To understand it, you need to understand this concept first, this sine wave, sunrise and sunset represented in the graph. To understand better, we take help of Fourier series and Fourier transform. Now, what is Fourier series and what is Fourier transform? This is what the actual frequency domain lies inside. So, in the nature, you see there are many periodic signals, many aperiodic signals. To extract the information inside a periodic signal, we go with Fourier series. To extract information from aperiodic signals, we go with Fourier transform. Now, what does these two things do? These two things gives the intensities of the signals at each and every frequency. Yes, this statement is complicated, but I'll make it clear in the further analyzations. Fourier series and Fourier transform will give the intensities of the signal at each and every frequencies. Now, this is very, very important. Just try to understand. You remember this point, like the frequency domain of a sine wave or a periodic wave having a frequency of something is represented like this. Every periodic wave will have a frequency. Let's take a sine wave only. Sine waves frequency spectrum is this, an impulse. Okay. Now, to understand Fourier series and Fourier transform, we need to take help of sine. To understand Fourier series better, we need to take help of sinusoid and cosines. Now, what is Fourier series? Fourier series is actually an approximation. Any periodic signal can be approximated by taking sinusoids and cosines as help, taking help of sines and cosines. If you add multiple harmonic cosines and sines together along with the DC component, you can approximate any periodic signal with respect to sines and cosines. That means you can able to represent any periodic signal by in terms of addition of sine and cosine harmonics. Now, this is little complicated, right? Now, let's directly go into the picture and we'll understand it. So, this is a square wave. What I mean to tell is any time domain periodic signal can be represented into frequency domain by taking multiple sinusoid and cosine harmonic additions. This is quite complicated. See, first, before entering into this concept, we need to understand what is meant by harmonics. What is sinusoid harmonics? What is cosine harmonics? Now, harmonics is something like whose frequency is an integral multiple of the fundamental frequency. Let's take this is a sinusoid. Now, this sinusoid, if it is this full cycle is represented in two full cycles, this is a second harmonic. If this full cycle is represented taking 3 full cycles, this is the third harmonic. Now, what I mean to tell is the Fourier series can be taken as these harmonics additions. If I take a periodic signal whose fundamental frequency is something, now those, let's take my fundamental frequency is, here the x is x. So here I'll take x as 2. So my fundamental frequency is 2. Now I can take the harmonics as an integer multiples, like I can take 1x, 2x, 3x, 4x, so that the main fundamental frequency will have the harmonics. Now if you add all these harmonics of sines and cosines from n going from 1 to infinite, that means you have to take an infinite number or a very large number to get error minimum. So that is what I have represented here. This is this square wave that you are seeing is a periodic time wave, which is periodic. Now what I have taken is this is a single harmonic, but now I have increased the harmonics and then I started to add them. Now slowly this addition of sine waves started to get into the shape of square wave. This is what the Fourier series. So if you see this, there is one harmonic, this is 2 harmonics, some other harmonics. If I add all of these things, we are getting another signal. Now this signal is the combination of all these signals. But how many harmonics you need to take? Only only depends on how many harmonics you take and try, so that the approximation error goes down. Now, what is the use of taking Fourier series and calling it to be frequency domain? I have told you before, you need to remember that the sinusoid time domain, frequency domain is just an impulse. Now, what are we doing here? We are approximating this time domain signal with respect to addition of harmonic sines and cosines. That means we are making the time domain signal, we are representing this time domain signal in terms of addition of harmonic sines and cosines. So we have sine x, sine 2x, sine 3x. Sine x means it has only one cycle, sine 2x means it has two cycles, which is second harmonics, sine 3x plus sine 4x, and so on until the shape gets clear. At the same time, we'll be adding cos x, cos 2x, cos 3x, like that. Now for cos x, what is the frequency domain? It's just an impulse. For cos 2x, it's another impulse. Cos 3x, it's another impulse. So if you take a periodic wave like this, and if you represent through a Fourier series by multiple addition of Fourier series and by multiple addition of harmonic sine waves and cosine waves, it only means the final wave can be expressed as the individual addition of the impulses at their own particular frequencies. This is what Fourier series explains. This is little complicated, but I'll make this simple in the further coming videos. I don't have a writing pad to explain by taking an example, but this is the formula that is taken to represent what is Fourier series and what is how well we can express through a mathematical formula. So any process can be represented taking graph as an example, and which internally can be explained taking a mathematical formula. So this is what it is, the Fourier series. And the Fourier transform, I'll explain you in the next video. To close this, I'll go with this explanation. So I have a square wave, and this is also approximated by multiple addition of sines and cosines. And I also have a sawtooth, which is also approximated taking multiple addition of sines and cosine harmonics. The same goes with the triangular wave and semicircle. Even a human face can also be done with proper addition. Any shape, any tree shape or anything can be analyzed or approximated using the Fourier series by carefully choosing how many harmonic additions you need to do. So the one thing you need to remember is Fourier series used for periodic signals. If you have a periodic time domain signal, to analyze it, to understand it in frequency domain, you need to have Fourier series, and you need to express it in a way that if you add the multiple harmonics of sines and cosine, you will be approximating, or you will be getting the time domain signal approximately. The more harmonics you take, less the error will be. This is the Fourier series for periodic signals, and the aperiodic signal frequency domain is the main thing that we need to concentrate, because you will never see any periodic signal in the nature. All laboratory signals that you see in your classrooms or laboratories are the periodic waves, because you can generate them with a particular frequency. The process of getting a square wave is a signal, but how many times the square wave is being generated per second is the frequency. Same goes with any shape being a periodic. So the periodic signals of Fourier transform we'll see in the next video.